All right, now that we have hopefully a good understanding of what current and voltage are, it's time to do a little bit of math. So let's first make sure we have a really good understanding of what current is. And I'm going to use analogy of a couple of roads to try to make this a little bit clearer. So we've got two roads here. We've got one road on the left-hand side that has a single lane of traffic, and the other one has 4 lanes of traffic. Now, let's say, for example, that cars are traveling the exact same speed on both roads. Now, the question is, which one has more cars go by every minute? Well, I think this is something that every one of us can probably visualize pretty easily. The likelihood is, if cars are going the same speed on both roads, and this road has 4 times as many lanes, then the number of cars going by every minute in this or on this road is going to be probably 4 times as much as on this one. And current basically works the same way. So the idea of current is we are counting the number of electrons that are going by in a circuit every second. We're not counting how fast they travel, we're counting how many. All right, so when you think about current, think of it like these 2 car lanes or these 2 roads, single lane versus a 4 lane road. Speed isn't what is important. The number of cars that go by every second is what is important. And in the case of current, we are talking about the number of electrons. So current is the number of charges or electrons that go by every second. And we measure that using Q, which is the quantity of charge, over time measured in seconds. All right, so I is our current, that is measured in amps. Q is our charge in coulombs, is what it's measured in, and T is our time. So if we know any 2 out of the 3 of these, we can figure out the third. So if we knew the amount of, or the number of charges that go by, and we knew the time that they go, or the amount of time it takes them for them to go by, we can then calculate the current. Now let's look at an example. So again, current I is equal to the charge passing by a point, Q, divided by time in seconds. Now let's say, for example, if we have 9 coulombs of charge pass a point in a circuit in 3 seconds, what's the current? Well, I is equal to Q divided by T. So I is equal to 9 coulombs divided by 3 seconds, which is equal to 3. So 9 divided by 3 is 3. That means that the current at that particular point in the circuit is 3 amperes. Okay, so let's look at current in series circuits and voltage in series circuit first, and then we'll look at both of them in parallel circuits. So here's a series circuit on the right. We've got a battery, we've got a couple of lamps, and we've got a switch. Now, in a series circuit, a reminder, the current flows one way through all of the components, and it is one continuous loop. It starts at the power supply and ends back at the power supply. So the electrons will come out of the battery, they will go through the circuit, and they will come back into the battery at the end of it. If there is a break in the circuit at any time, at any point, then the current will stop flowing to all of the components. All right, so this switch is open, which means nothing gets any energy. Right? The electrons do not go into the battery. The electrons do not gain energy. The lamps do not take energy from the electrons to light. Nothing happens. Okay, that's an important idea to think about when we get into actually calculating the current in a series circuit. Since there's only one possible pathway for the electrons, that means the current has to be the same everywhere. So if an electron comes out here and travels through the circuit and goes through a lamp, and then back in, however many electrons go by here has to be the same as here, has to be the same as here, same here, same here, same here. Right? The current in a series circuit has to be the same everywhere. So what that means that the current at any point will equal the current at any other point in the circuit. So I1 could be a measurement taken here, I2 could be a measurement taken here, I3 could be a measurement taken here. It doesn't matter. The current will always be the same in a series circuit because there's nowhere else for the electrons to go. Now, an example. So the current at the battery in this circuit is 3 amps. What is the current at the first light bulb? Well, let's call this the first light bulb. All right, so the current at the battery is 3 amps. What's the current here? Well, since the current has to be the same everywhere, that means that the current at the battery is 3 amps, then the current here must also be 3 amps. Okay? Now, what's the current at the switch? The same, right? Same idea. It doesn't matter where you are in the circuit, it will be the same. Now, I will point out that this is an open circuit right now, which means technically the current at the entire circuit is 0 because there's no flow, but let's assume that that switch was actually closed. All right, so then the current there would also be 3 amps. All right, so now let's talk about what happens to voltage in a series circuit. Now, a reminder that a power source, so a battery or it could be a power pack that's plugged into the wall, is going to supply energy to the electrons that go through it. Every electron that goes through the battery will get the same amount of energy. So if I have a 9-volt battery, that means every electron that goes through the battery will gain 9 volts of energy. Now, every electron must also lose all of its energy by the time it gets back to the battery. So that means no matter how many volts the electron gains as it leaves the battery, it has to lose it all and be down to 0 volts when it gets back to the beginning. So that means that the voltage of those electrons, that energy that has been given to those electrons, has to be spread out amongst all of the loads. If all of the energy went to this light bulb, then this light bulb would never turn on. And I think we've all seen lights in a series circuit. When one light goes on, they all go on. All right, so that means that that energy has to be shared between each item in the circuit. All right, so here is our basic equation, or our basic way to calculate the total voltage or the voltage of any individual load in a series circuit. The total voltage, or the voltage at the battery, so you see this little 0, all right, so you can refer to this as V0. Sometimes you'll see it or hear it referred to as V0. That is the voltage of the source of the energy, so the voltage of the battery. It is going to equal the sum of all of the voltages of everything else in the circuit. Now, something to be careful about. That doesn't mean that every load in the circuit has the same voltage. It just means that they are each going to get some of the voltage. All right. So if I had a light bulb and a motor in a circuit, the light bulb might get more than the motor, or the motor might get more than the light bulb. It'll depend on the properties of the light bulb and the motor. However, if we have two identical bulbs, all right, so if these two bulbs are the same, then they will have the same voltage. All right. Now, let's look at an example. So let's say the voltage across each of the light bulbs in this circuit is 2 volts. What's the voltage across the battery? Well, here is our basic equation for this. The total, or the voltage of the battery, will equal the voltage of one load plus the voltage of another load. In this case, it's our 2 lamps. Now, we know that the voltage of each of the lamps is 2 volts from the question. So that means the total has to equal 2 volts plus 2 volts. So that tells us that the voltage of this battery has to be 4 volts. All right, so that's series circuits. Let's talk about parallel circuits. Well, in a parallel circuit, a reminder, we have current flowing through different branches with components in them. So we have more than one pathway for the electrons to travel. So in this case, we have electrons that would come out here. The electrons would hit this point where they can branch. They can go into this direction or this direction. Either way, they're going to go through a load, come back to this point, join back together, and then go back to the battery. And again, a reminder, electrons are always going to go in the direction towards the battery. They're never going to go in the they're never going to go against the flow. Now, if there is a break in one branch of a circuit, that doesn't affect the other one, all right? The other one will still continue to have electrons flowing through it. Okay, now let's talk about what actually happens to the current in a parallel circuit. Since there's more than one pathway for the electrons to travel, that means the current has to spread out through all the paths. Right? Think of it like a river. So this is the river flowing along, and it hits a giant rock or an island in the middle of the river. Well, some of the water is going to go one direction, some of the water is going to go the other direction, and then they'll meet up on the other side of the island or the rock and then continue on in the river. All right, so that means that whatever the current is here, it has to be split up in between these two pathways. Right, and then over here, they will join back up and the current will continue along as it was before. Now, here is how we actually determine what the current is at any point in a parallel circuit. The total current, and we typically measure the total current right around the battery, so typically right in front of or right after the battery. All right, so the total current is going to equal the current in each of the pathways added up together. Now, take a look specifically at this drawing. If I were to take a measurement of the current here and the measurement of the current here, they're going to be the same because the electrons haven't gone anywhere. There's no other pathway for them to follow. But as soon as I hit this position here, we're going to have some of the electrons go this way and some of the electrons go this way. Now, it could be an equal number going in each direction, but it's going to depend on what these loads are. It could be some of it going this way and a lot going this way, or it could be a lot going this way and only a small amount going this way. It's going to depend. But the total current between these two pathways will add up to what the current was here. All right, so let's look at an example. Let's say the total current of this circuit is 5 amps. So if I take a measurement right here, it's going to tell me that the current is 5 amps. And the current at lamp number 1 right here is 3 amps. Well, then what's the current at lamp number 2? Well, I have 5 amps here, 5 amps, 5 amps, 5 amps, 5 amps, and then at this point here, some of the current, so some of the electrons will go this way, and some of the electrons go this way. So if 3 amps go this way, how much is going to go that way? Well, look at our little equation. I0 or I0, or the total current, is going to equal the current at lamp 1 plus the current at lamp 2. So we know the total current is 5 amps. We know the current at lamp 1 is 3 amps. And we're trying to figure out what the current is at lamp 2. So now we've got 2 of these values put in. We just have to figure out the third. So this I2 is going to equal 5 amps minus 3 amps, which gives us a total current of 2 amps. All right. Now, for voltage in parallel circuits, well, every electron needs to get rid of all of its energy by the time it gets back to the battery. We've already mentioned that a few times. That means that no matter which pathway an electron takes, it has to get rid of all of its energy. So if an electron travels here and goes through this lamp and goes back, it has to get rid of all of its energy at this lamp. If an electron goes this way and travels through this lamp and then comes back, it has to get rid of all of its energy at that lamp. All right, so no matter which pathway it takes, it has to get rid of all of the energy on that pathway. That tells us that each of these pathways has to have the same voltage as the battery. All right, so our general equation is V0 or V0 is equal to V1 is equal to V2 is equal to V3, which means the voltage of the battery is going to equal the voltage in pathway 1, which is going to equal the voltage in pathway 2, it's going to equal the voltage in pathway 3, etc., etc., etc. Okay? Now, let's try an example. Let's say the voltage across lamp number 1 and lamp number 2 is 6 volts. So lamp number 1 has a voltage of 6 volts, lamp number 2 has a voltage of 6 volts. What was the voltage of the battery? Well, if V naught, or the voltage of the battery, is going to be equal to V1, it's going to be equal to V2, that means that since each of the lamps has a voltage of 6 volts, that tells us that the battery must be 6 volts. Now, this may lead to a couple of questions for you. Number one might be, well, what happens if each of these lamps isn't identical? What happens if they are two different lamps? Well, that's not going to matter. It doesn't matter what that lamp looks like or is made of, it is going to have to use up 6 volts of energy. And this is where people sometimes have trouble with changing light bulbs in circuits. If you use the wrong bulb, you might end up overheating it and blowing it out, because this is going to get 6 volts whether it likes it or not, because this is a 6-volt battery. All right, so an electron will come out, it'll hit this light bulb, and it's going to get rid of all of its energy. If this light bulb can't handle 6 volts, it's going to burn out that battery. It's going to burn out that light bulb. All right. Another question that some of you might be coming up with is, well, what happens if there's more than one bulb on this pathway? So this pathway has one bulb, and it is going to use up all 6 volts of energy. If this pathway has another light bulb added on, what's going to happen? Well, this is where we get into what we talked about right at the very beginning when I said there are 3 types of circuits. There are series circuits, there are parallel circuits, and there are complex circuits. If I were to add a bulb to this, that would make this a more complicated circuit. All right, this would be a complex circuit, and we'll get into that in a little bit as we get a little bit further in. But just to quickly answer the question, if this is 6 volts and this is 6 volts, that means that this pathway has to use up 6 volts. So if there's one light bulb in here, it would be a 6-volt light bulb. If there are 2 light bulbs in this pathway, that means each one is going to have to share the voltage, and if they're identical, that means one would be 3 and the other would be 3. So it basically turns this section into a series section. All right? It can get very complicated as we get farther along. We'll see that as we go farther.